Welcome to this video. Today, we'll be diving into LeetCode problem number 2220, minimum bit flips to convert number. This problem challenges us to compute the minimum number of bit flips required to transform one integer into another. It's a fascinating exercise in bit manipulation and binary representation, so let's get started. In this problem, you are given two integers, called start and goal, and your task is to determine the minimum number of bit flips required to convert the binary representation of start into the binary representation of goal. A bit flip means changing a single bit from 0 to 1, or from 1 to 0. For example, if a bit is 1 in start but 0 in goal, flipping that bit will make the two numbers match at that position. The input consists of two integers, start and goal, where both values range from 0 to 10 to the power of 9. The output is a single integer representing the minimum number of bit flips needed to achieve this conversion. Let's look at the first example. Here, the input values are start equals 10 and goal equals 7. The binary representation of 10 is 1010, and the binary representation of 7 is 0111. To convert 1010 into 0111, we need to flip three specific bits. First, the first bit changes from 1 to 0. Second, the second bit changes from 0 to 1. Finally, the fourth bit changes from 1 to 0. These three flips make the two binary numbers identical, so the output for this example is 3. This demonstrates how flipping individual bits aligns the binary representations. Now, consider the second example where start equals 3 and goal equals 4. The binary representation of 3 is 0011, and the binary representation of 4 is 0100. To convert 0011 into 0100, we need to flip three bits. The first bit changes from 1 to 0, the second bit also changes from 1 to 0, and the third bit changes from 0 to 1. After these flips, the binary representation of start matches the binary representation of goal. Therefore, the output here is also 3. This example highlights how the number of differing bits directly determines the number of flips required. Now let's look at the third example. Here, both start and goal are equal to 0. The binary representation of 0 is simply 0, and since both numbers are identical, no bits need to be flipped. As a result, the output is 0. Additionally, some edge cases help clarify the problem further. For instance, if start and goal are the same, the result is always 0 because no changes are necessary. Another edge case is when one of the numbers is 0. In that scenario, the output is the number of ones in the binary representation of the other number. Finally, the solution must also handle large values of start and goal, up to 10 to the power of 9, efficiently. To solve this problem, we can use the XOR operation, denoted as caret. The XOR operation is particularly useful here because it produces a binary number where each set bit, or 1, represents a position where the bits of start and goal differ. For example, performing start caret goal directly identifies which bits need to be flipped. To determine the minimum number of bit flips, we simply count the number of ones, or set bits, in the result of start caret goal. The time complexity of this approach is O log max start goal, which corresponds to the number of bits required to represent the larger number in binary. The space complexity is O(1), as the solution requires only a constant amount of space. This makes the method computationally efficient and well suited for the problem constraints. To solve the problem of finding the minimum bit flips needed to convert one number to another, we can start by understanding the concept of a bit flip, changing a binary bit from 0 to 1, or from 1 to 0. One approach we could take is the brute force method. Here, we convert both numbers into binary strings, ensuring they are of equal length by padding the shorter one with leading zeros. Then, we iterate through the bits of both strings, comparing each position to count the mismatches. Each mismatch represents a bit flip. While this approach is straightforward and easy to understand, it introduces unnecessary overhead from string conversions and padding. Additionally, iterating through binary strings is less efficient when compared to leveraging bitwise operations. Thus, while the brute force method is valid, it is suboptimal in terms of performance and scalability. A more efficient method is the optimized bitwise approach, which is the chosen solution. The key insight here is that a bit flip is required only when the bits at corresponding positions in the two numbers differ. Using the XOR operation, or caret, we can directly identify these differing positions. The XOR operation gives a result where each bit is 1 if the corresponding bits in the two numbers are different, and 0 if they are the same. From this result, we simply count the number of ones, as each one represents a bit flip. To count the ones, we can use the built-in function bin XOR_result.count 1 for simplicity, or use a bitwise trick to clear the least significant one repeatedly while counting iterations. This approach is efficient, with a time complexity proportional to the number of bits in the larger number, or O, log, max, start, goal. It avoids unnecessary overhead like string manipulations and provides a clean, elegant solution using direct bitwise operations. Another way to view this problem is through the concept of Hamming distance, which measures the number of differing bits between two binary representations. The XOR operation essentially reduces the problem to calculating this distance. Additionally, some programming languages offer a population count function, or popcount, which can directly count the number of ones in the XOR result, making the implementation even more concise. Among all these approaches, the optimized bitwise solution stands out as the most efficient and practical. The insight that XOR directly identifies differing bits was the pivotal realization, allowing us to compute the result in O, log, max, start, goal time. Compared to the brute force method, it eliminates unnecessary overhead and is faster and cleaner. Alternative methods like Hamming distance or popcount offer similar conceptual solutions but might depend on language-specific features. Ultimately, the optimized bitwise approach is the best choice for its balance of efficiency, simplicity, and minimal code requirements. To solve the problem of finding the minimum number of bit flips required to convert one integer into another, we start by understanding the concept of a bit flip. A bit flip changes a binary digit from 0 to 1, or from 1 to 0. The goal here is to determine how many bits differ between the binary representations of two integers, start and goal. The key insight is to use the XOR operation, which is represented by the caret symbol. XOR is ideal for this task because it compares two bits and returns 1 if they are different and 0 if they are the same. Applying XOR to start and goal produces a binary number where every one indicates a differing bit. The next step is to count how many ones are present in this XOR result, as that will tell us the number of differing bits, or bit flips, needed to transform start into goal. We can now break the solution into step-by-step execution. First, compute the XOR result using start caret goal. This result will highlight the positions where the two integers differ. Next, initialize a variable, bit_flips, to 0. This counter will keep track of the number of differing bits. To count the ones in the XOR result, we use a loop. While the XOR result is not 0, check if the least significant bit is 1 using the expression XOR_result and 1. If it is, increment the bit_flips counter. Then, right-shift the XOR result by 1 using XOR_result equals 1 to examine the next bit. Repeat this process until all bits are processed. At the end, return the value of bit_flips. For a more optimized approach, we can use a trick with n and n1. This trick directly removes the least significant one from the XOR result, allowing us to count the ones more efficiently, reducing the number of iterations to the exact number of differing bits, or the Hamming weight. Now, let's summarize the optimized algorithm. Start by computing the XOR result as XOR_result equals start caret goal. Then, initialize a counter, bit_flips, to 0. While the XOR result is not 0, increment bit_flips and update XOR_result using the expression XOR_result equals XOR_result and XOR_result 1. This operation removes the least significant one from the binary representation of XOR_result. Repeat this process until the XOR result becomes 0. Finally, return the value of bit_flips. There are a few key insights to take away here. First, the XOR operation is an efficient way to identify differences between two binary numbers, as it directly highlights differing bits. Second, the n and n1 trick is a powerful optimization that skips unnecessary iterations by focusing only on the set bits, significantly improving efficiency. Lastly, this algorithm handles edge cases gracefully. For example, when start equals goal, the XOR result is 0, and no flips are needed. Additionally, the algorithm scales well even for large numbers since its performance depends only on the number of differing bits, not the total number of bits. This algorithm requires minimal data structures. Specifically, we use two integer variables, XOR_result to store the XOR of start and goal, and bit_flips to count the number of differing bits. These variables are sufficient because the algorithm operates directly on the binary representation of the numbers. Analyzing the complexity, the time complexity of the optimized approach is O(k), where k is the number of differing bits, or the Hamming weight of start-goal. This is much more efficient than a naive O(n) approach, where n is the total number of bits in the integers. For space complexity, the algorithm uses O(1) auxiliary space, as only a few integer variables are required. This efficiency makes the solution both time and space optimal. Let's walk through an example to see the algorithm in action. Suppose start is 10, which is 1010 in binary, and goal is 7, which is 0111 in binary. First, compute the XOR result, 1010-0111, which equals 1101 in binary. Next, initialize bit_flips to 0. Now, process the XOR result. In the first iteration, the XOR result is 1101. Increment bit_flips to 1 and update the XOR result using 1101 and 1100, which gives 1100. In the second iteration, the XOR result is 1100. Increment bit_flips to 2 and update the XOR result to 1100 and 1011, which results in 1000. In the third iteration, the XOR result is 1000. Increment bit_flips to 3 and update the XOR result to 1000 and 0111, which yields 0000. At this point, the XOR result is 0, so the loop ends. The final value of bit_flips is 3. The output of this example is that the minimum number of bit flips required to convert 10 into 7 is 3. This result aligns with our step-by-step execution and demonstrates the efficiency of the algorithm. By leveraging the XOR operation and the n and n1 optimization, we've minimized the computational overhead while solving the problem accurately. This solution focuses on efficiently calculating the minimum number of bit flips required to convert one integer, start, into another integer, goal. Let's break down the code step by step. 1. XOR operation asterisk the line XOR_result equals start_goal computes the XOR, exclusive OR, of start and goal. The XOR operation produces a binary number where each bit is set to 1 if the corresponding bits of start and goal differ, and 0 if they are the same. This step effectively identifies all the differing bits between start and goal. 2. Counting set bits asterisk the line bin XOR_result count 1 calculates the number of ones set bits in the binary representation of XOR_result. Each one corresponds to a differing bit between start and goal, which represents a bit that needs to be flipped. To do this, the bin function is used to convert XOR_result into its binary string representation, and the count method is used to count the occurrences of 1. 3. Return statement asterisk the function directly returns the count of differing bits, which is the minimum number of bit flips needed to convert start to goal. ###key insights. Using the XOR operation ensures that we only need a single operation to detect differing bits, making this approach highly efficient. Counting the ones in the binary representation is straightforward and leverages Python's built-in string manipulation capabilities. ###complexity. Time complexity asterisk the XOR operation and the conversion to binary representation both operate in O log n, where n is the maximum of start or goal. Space complexity asterisk the space used is minimal, as we only store a single integer, XOR_result, and its binary string representation temporarily. This solution is concise, efficient, and handles all valid inputs, including edge cases where start and goal are the same, resulting in 0 flips, or completely different, resulting in the maximum number of flips for their bit width. This is the Java implementation of the minimum bit flips to convert number problem from LeetCode. The logic mirrors the Python solution, leveraging the XOR operation to identify differing bits between two numbers. The while loop efficiently counts the number of differing bits using bitwise operations. Key differences from Python include explicit type declarations and the use of Java's unsigned right shift operator to handle binary manipulation. To solve this problem, we start by determining how many bits differ between the numbers start and goal. First, we use the XOR operation, which compares the binary representations of the two numbers bit by bit. If the bits are different, the result is 1, if they are the same, the result is 0. For this example, where start is 10 and goal is 7, the binary representation of 10 is 1010, and for 7 it is 0111. Performing the XOR operation gives us 1101 in binary. Next, we count how many 1s are present in the XOR result. Each one represents a bit that needs to be flipped to convert start to goal. Using the built-in function bin XOR_result.count 1, we determine that there are 3 ones in the binary result 1101. Therefore, the minimum number of bit flips required is 3. Now let's look at another example where start is 8 and goal is 3. Again, we begin with the XOR operation. The binary representation of 8 is 1004.3, it is 0011. Performing the XOR operation, we get 1011 in binary. This result shows us which bits are different between the two numbers. To find out how many flips are needed, we count the 1s in the XOR result. The binary 1011 contains 3 1s, so the minimum number of bit flips required to convert start to goal is also 3 in this case. In this example, we consider the case where start is 0 and goal is 15. The binary representation of 0 is 0000 and for 15, it is 1111. Performing the XOR operation on these values gives us 1111 in binary. This indicates that all the bits in start differ from those in goal. To determine how many flips are required, we count the 1s in the XOR result. The binary 1111 contains 4 1s, meaning that every bit needs to be flipped. As a result, the minimum number of bit flips required is 4. This approach works because the XOR operation identifies exactly which bits differ between two numbers. Counting the 1s in the XOR result directly tells us how many bits need to be flipped to transform one number into the other. This method is very efficient since both the XOR operation and counting the 1s can be performed quickly, with a time complexity of O(n), where n is the number of bits in the numbers. By following these steps, we can reliably and efficiently calculate the minimum number of bit flips required for any start and goal values. To analyze the time complexity of the algorithm, we start by considering the 3 main operations involved. First, there is the XOR operation, where start is XOR'd with goal. This operation works by comparing the binary representations of the two numbers bit by bit. The time complexity for this step is O(k), where k is the number of bits needed to represent the larger of the two numbers. In most practical scenarios, k is constrained by the word size of the machine, such as 32 or 64 bits for standard integers. Next, the bin function is used to convert the result of the XOR operation into its binary string representation. This conversion also takes O(k) time, as it processes each bit in the XOR result to generate the string. Finally, the .count 1 method is applied to the binary string to count the number of ones, which represent the differing bits between start and goal. This operation scans through the binary string, contributing an additional O(k) to the time complexity. Together, these steps demonstrate a clear linear relationship with respect to the number of bits, k. When we consider the overall time complexity, all 3 operations XOR, binary conversion, and counting ones are linear in relation to the number of bits, k. This means the total time complexity is O(k). However, since modern systems work with fixed-size integers, such as 32 or 64 bits, the value of k remains constant in practical scenarios. As a result, the effective time complexity is O(1). Shifting focus to space complexity, the XOR operation itself produces a single integer result, so it requires only O(1) space. The bin function, on the other hand, generates a binary string representation of the XOR result. The length of this string is proportional to the number of bits in the XOR result, which is O(k). For fixed-size integers, however, this space usage is bounded and can also be considered constant. The .count 1 operation works directly on the binary string without additional storage, meaning it has an extra space requirement of O(1). Overall, the algorithm efficiently balances time and space usage. Summarizing the space complexity, the algorithm relies on OK space for the binary string representation of the XOR result. However, for fixed-size integers, this is effectively O1 in real-world scenarios. Let's consider how this compares to a naive or brute force approach. A less optimized method might iterate through each bit of start and goal, performing manual comparisons to count the differing bits. While this also has a time complexity of OK, it lacks the elegance and efficiency of the built-in operations such as caret, bin, and .count used in the given solution. These operations are not only concise but also optimized for performance by the underlying system. Looking at best, average, and worst cases, the time complexity remains OK, because the number of operations consistently depends on the bit length of the input numbers. This uniformity ensures that all cases best, average, and worst are identical. Mathematically, the linear nature of each operation with respect to k solidifies the overall time complexity as OK. For fixed-size integers, this simplifies to O1, and the space complexity is also effectively constant, making the implementation highly efficient in all scenarios. When tackling this problem, there are several common mistakes to watch out for. First, misunderstanding the XOR operation can lead to errors. Remember, XOR is crucial because it directly identifies differing bits between two numbers, producing a 1 where the bits differ and a 0 where they are the same. Using addition or subtraction instead of XOR will not yield the correct result. Another common issue is not accounting for leading zeros. Binary representations of integers do not automatically include leading zeros, so if the bit lengths of the numbers differ, this can cause incorrect results unless you explicitly handle it. Lastly, manually iterating over bits to compare them, instead of leveraging bitwise operations, is inefficient. Efficient tools like XOR and bit shifting allow you to process the bits directly and avoid the overhead of converting numbers to binary strings or using loops unnecessarily. Another area where mistakes often occur is in calculating the number of differing bits. After performing the XOR operation, the result tells you which bits are different, but the number of differing bits corresponds to the number of ones in the XOR result. Forgetting to count these ones, or doing so inefficiently, can lead to problems. Fortunately, most programming languages offer built-in functions like bin, x.count, 1, in Python or __ built-in _popcount, in C++ to make this step simple and efficient. Additionally, watch out for off-by-1 errors, particularly in edge cases. For example, when the start and goal integers are equal, the answer should be 0 because no flips are required. Failing to explicitly handle this case may result in incorrect outputs or unnecessary operations. In an interview setting, this problem provides a great opportunity to showcase your understanding of bit manipulation. Operations like XOR, AND, OR, and bit shifting are fundamental skills that interviewers often test. The key here is to demonstrate how XOR can be used both to identify differing bits and to streamline the process of counting them. Efficiency is another important consideration. While the problem has a clear solution, interviewers may evaluate your ability to minimize operations and explain the time complexity of your approach. For instance, the XOR method operates in OK time, where k is the number of bits in the larger number. It's also important to clearly articulate how you handle edge cases, such as when start equals goal, or when dealing with very large or negative numbers if applicable. Finally, you can impress interviewers by connecting this problem to real-world applications, like cryptography, network protocols, or low-level system programming, where bit manipulation is often used. This problem is closely related to several other LeetCode problems, which can help reinforce your understanding of bit manipulation. For example, LeetCode 461, Hamming distance, uses a similar concept of counting differing bits between two integers with XOR. LeetCode 191, number of 1 bits, focuses specifically on counting ones in the binary representation of a number, which is a key step in this problem as well. LeetCode 136, single number, demonstrates how XOR can be applied to find a unique element in an array where all other elements appear twice. Finally, LeetCode 476, number complement, involves flipping all the bits of a number within its binary length. Studying these related problems can deepen your understanding of bitwise operations and prepare you for variations in interview scenarios. There are multiple approaches to solving this problem, each with its own trade-offs. The optimal approach relies on bitwise operations. By using XOR to identify differing bits and counting the resultant ones, you achieve the best efficiency with a time complexity of O(k), where k is the number of bits and the larger number. The trade-off here is that it requires a solid understanding of bitwise operators. Alternatively, you could convert the numbers to binary strings, pad them to the same length, and compare the bits one by one. While simpler to implement, this method is less efficient due to the overhead of string operations, even though the overall time complexity is still O(k). Lastly, a manual iteration approach involves using bit masking and shifting to compare bits individually. This method may be easier to understand conceptually but is more verbose and prone to errors compared to using XOR. Choosing the right approach depends on your familiarity with bitwise operations and the constraints of the problem. Thank you for watching. In this video, we learned how to solve LeetCode problem number 2220 by using an efficient bitwise approach. We reviewed the algorithm, time and space complexity, and key takeaways. If you enjoyed this or found it helpful, please like, subscribe, and join us for more problem-solving videos. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!